Hey, hi. This is Sam Sandoval, and this time we're going to be talking about an introduction to benefit cost analysis. This is part of one of the topics that you will be seeing, and this is part of your class of ESM-121, Water Science and Management. So let's start talking about this topic. So as you will imagine, in this time we're going to be talking about benefit, well, how to estimate benefit and costs. And out of these two, once we have analyzed these two, we're going to be also talking about a specific um, um, calculation that is called net benefits. So what do you think are the net benefits? Yeah, as you may have been imagined, the net benefits are actually the benefits minus the cost. So that's what we are. So the net benefits are actually the benefits minus the cost. So what do you think are the values? If we're analyzing these net benefits, um, what what is the value that the net benefits should have in order to evaluate a specific project to be economically feasible? So imagine that you are evaluating a project, and when you are evaluating a project, you would like to know if that project is economically feasible. So if the net benefits are greater than zero, greater than zero, it means that the benefits outnumber the cost. So in this case, the project is actually economically feasible. Otherwise, if the net benefits are less than zero, then actually the project is not economically feasible. Another way also to estimating this is actually something that is called the benefit cost ratio. What that means is that you divide the benefits over the cost. And once you divide these benefits over the cost, if this ratio is greater than 1, then similarly, the project is economically feasible, meaning that the benefits outnumber the costs. Likewise, if this ratio is less than 1, then in this case the project is not economically feasible, meaning that the cost outnumber the benefits. So this is what we're going to be talking today. I'm going to show you a little bit of engineering economics and also specifically how to compare two projects and then the incremental net benefit method. So why do we estimate uh, net benefits? Well, first, there is a need for, or why do we estimate the economic value of a project? First, there is a need for water, and this is becoming more acute. We have governments and investors, and what they do is basically they develop water resources and they analyze the expenditures are large. So you have imagined that you have to choose among different alternatives, and when you are doing that, well, number one is that the money that you are investing or that you are planning to invest should be used efficiently. It should meet the needs of stakeholders and it should spend wisely. So, what are the goals of this lecture? These parts will be to show you how to estimate costs and benefit. Um, in this case, um, when you're planning for a project, part of the goals is to ensure that this project use the capital wisely. The other part is to provide a framework. So in this case, you want to compare apples to apples, and how to do that? Well, basically, you estimate the annualized cost of two different projects, and then you figure out, okay, yearly on average, I'm going to be spending this much in this project compared to this much in this project. So that's really what you want to estimate, and also the impacts of some regulatory changes. What is the basic principle, as I mentioned before? That the benefits must exceed the cost. And again, as I was talking to you, this is a definition that you should also learned by heart, that the net benefits are equal the benefits minus the costs. Okay, so let me actually explain a little bit of these discount rate formulas, interest rate formulas. And in this case, the idea is that you're going to be using these formulas, and I strongly recommend you that what you do is write it down for the exam. Um, and in this case, this is what it's. Um, this is the first part. So for these discount rate formulas, what you really want to know is, well, we're going to have different variables: present value, future value, and a specific annualized value. We can convert from present to annual from when we are planning to do this, converting from a present value to an annual value. Then we use this formula. When you plug the annual estimate that you have, I is the, let me actually write down here some of the terms. So P, as I was mentioning, is the present value. F is the future value. And then A is the annualized value. Okay. Now, I, it accounts for the discount rate. So I is the discount rate, and T is the time in years. So once I have explained all of this, so let's say you want to know in present value what is a specific future value of something. So you use this formula. When you plug this future value, this discount rate, and the number of years that this value is ahead of this of today. Similarly, if you want to estimate what is the present value of a specific analyzed expenditure, then you do the same. Plug this analyzed expenditure, 1 plus the discount rate, to the time power in years, minus 1, and so on. Now, the second part is actually how to, and this is how to convert something, a future or an annual value, into a present value. Similarly, how to convert, in this case, a present and an annual cost into a future value. And then again, here in this case, well, you just use these formulas. And you're going to see that, I mean, at this point, this may sound a little bit abstract, but as I'm going to give you some examples, you're going to see why these formulas are useful. And finally, how to convert two annual values. And again, given that you may have some present values, or that you may have also some future values. So let me erase this. Okay, so let me show you how these formulas are used. So let's start simple. Imagine that you have $100 and that you are investing those $100, and that the bank tells you that you will receive a 5 annual, in this case, interest rate. So if you have $100 and they are telling you that you have a 5% interest rate at the end of 1 year, how much money are you going to be receiving? So in this case, you will be expecting to receive 5% more of your initial savings of your initial value. In this case, you will be expecting to receive $105. Again, we can actually rewrite this by saying that in the future, by the end of year 1, that's why it's in the future, for year 1, I'm going to be planning of 100 years that I'm spending, of that I'm actually investing today. What will be the future value of these $100? Well, you can actually, what we're using is this equation. And basically what we're doing is 1 plus the interest rate. Now let me actually explain you this a little bit more um, before actually just copying these equations ideally. So this is at the end, or just without thinking about it. So this is at the end of the first year. At the end of the second year, what you would be expecting is to, let's say that you reinvest this $105. At the end of the second year, following the same logic, you will be expecting to receive 5% more of this 100% of $105. So in this case, it will be 110.25. So as you may think, as the amount of money that you are accumulating and it's receiving the same interest rate, so this value is going to be greater and greater. The logical is that if you invest $100, the first year it's going to be 105, the second year 110, and as you can see here, because you're investing a little bit more, you're going receiving some extra dollars. So that's what we have in there. Now let me actually explain you this, or elaborate on this equation. This 105 for the same ID at the end of the second year. So this 105 is actually this. And actually, if you think about why do I know that this 105 is this, because basically it comes from here. Can you see? Now this is times this 1 plus 0.05. So this is how we get to this 110.25 that we estimated before. So basically, this 1 plus 0.05 times 1 plus 0.05, this is a common factor. And basically, we can express it like this. So that is actually how this equation, which that was the one that I was telling you, this 2.1, how you can actually derive it. Okay, so let's start thinking about, let's actually, what I'm going to be doing is start using these equations, or I'm going to provide you some examples of how to use these different formulas. That's basically what I'm going to do in the next 10-15 minutes. So in this case, imagine that I want to know, well, this is um, um, the um, the background of this. So during the Mexican War in 1988, the U.S. paid, well, basically for all this territory, it paid about 11 cents per acre in 1948. And basically that's what it says in there. That's basically how, when if you read the Guadalupe Hidalgo Treaty, that's what they say, how much they are going to pay. So 15 millions for about 201 square miles. So let's consider a 6% discount rate. Is paying 11 cents per acre too much or too few? So in this case, what we really want to know is how these 11 cents, what is the value of 11 cents in present dollars? So what I'm going to do is to say, like, okay, I'm gonna sit myself here in 1848, and I'm gonna say, okay, how much these 11 cents represent now in 2016? Okay, so what I'm going to do is to use, I think this is equation 2.1, and yeah, this is equation 2.1, and basically what I'm going to do is just applying it. So this is, in this case, equation 11.1 tells you, okay, this is this present value, this is the discount rate, and this is the number of years, which is basically 2006 minus 1848, 168 years. So this translates into almost $2,000 per acre. So is this too much or too few? Actually, now we know that those 11 cents per acre in today's dollars, they are about $2,000. So the current value in some of these places is on average 50,000 um, acres per $50,000 per acre. So as you can see, it was a very good bargain. Now let's actually think that you, as a very wise and cautious student, you are saving about $1,000 every year during 10 years, since you start your bachelor's all the way until you finish your PhD. So let's think that you're gonna do that. So how much all these savings will convert once you are done with these 10 years and you receive all this money that you have been saved in one exhibition? I mean, ideally you will say, well, if I'm investing $10,000 every year times 10 years, I will be receiving approximately 10,000 or more. So what do you think? Actually, can we know exactly how much money will that be in the future? Of course, yes. And in this case, we're using formula 2.2, which is basically substituting that formula, which is basically, here is the annualized money that we are saving every year, um, the discount rate here, the number of years, and it is about $8,000, $11,000 of what you're going to receive. So as you can see, I mean, that is a very good deal. Okay, so this is how to use those two formulas. Again, this is 2.1, and this is how you can use formula 2.2. Now let's move to present value. And in this case for present value, we're going to be talking about, well, formulas 1.1 and 1.2. So let's say that you're going to be receiving that at some point in the future, you know that you're going to be receiving $1,000. I don't know, your mom or I don't know, your grandma tells you, hey, when you finish your bachelor's, your major, I'm gonna give you $1,000, and that is 3 years ahead of you. So actually, how much money does that $1,000 represent in today's um, um, uh, in present value? So basically, um, only for 1 year, if this is 1 year ahead, $1,000 represents at 1.5 discount rate, it represents only $985. And in this case, the formula that we're using is formula 1.1. So as you can see, I mean, and this is consistent. Basically, what it's telling you is that, I mean, even though you're going to be receiving $1,000 in the future, I mean, that amount of money is actually less in present value. The second year, I mean, if you will be receiving it, I mean, 2 years ahead, actually that is less. Those $1,000 that your, I don't know, relative will give you, in today's dollars, they are actually represent the same, and so on. Now, let's say that you're going to be receiving a pension annually and for 12 years. And this pension is about, let's say that is $1,000 every year. For imagine that for some reason you're receiving this much money. So in this case, what about if the interest rate in this case is only 1%? Okay, What will be if all during all these 12 years you receive all that money and you put it in here today and you pilot all of that? So in this case, using this, well, this is formula 1.1 and this is formula 1.2. So in this case, when you substitute these values into this formula, basically what you get is that actually out of those 12 years, if you were receiving all that amount, it's going to be only in today's value only 11,000, which again, as you can see, I mean, the same, well, when you're thinking of a fixed amount in the future, when you move that fixed amount to the present, it actually, it its present value is less. Um, why? Because we think, I mean, actually, things as they progress, their value increase more and more. Now, um, let's go to this one, which is one of my favorites. So, I mean, who doesn't want to buy a Mini Cooper? Come on, guys. I mean, all of you, I'm pretty sure that at some point have thought about how cute it looks, a Mini Cooper. So, in this case, let's think about what will be the if a Mini Cooper, um, I mean, its value is about 30 grand, and the annual interest rate is about, the discount rate is about 9% per year, and you're planning to, and um, you're planning to pay it in 5 years. Um, how much these $30,000? How much are you gonna be paying annually and monthly, given that you have all these numbers? And I'm pretty sure that every time that you go to the car dealer, I mean, they bore you with this. Well, now you know how actually how to do the math. And in this case, this is formula 3.1. Okay. So in this case, I mean, you basically substitute the formula here, the present value, the discount rate, the number of years, and so on. So basically, in order to pay for these $30,000, you actually need to be paying annually, or the expected annual cost is about $6,163. So that is actually a nice bargain. In your exercise, you're going to be doing something like this, but you're going to see that, well, and if you divide this amount over 12 months, you're going to see that, I mean, the value of a Mini Cooper is about, in this case with these specific numbers, $514 a month, which is actually not that expensive. What you're going to see is that they later are at you, when you go to a dealership, for every $1,000 that you are actually borrowing out of them, they will add you an extra cost. And that is actually when things will start going a little bit pricey. That's what you're gonna be start seeing. And well, again, in this case, consider that well, basically, I mean, this is their business, and always to read the small letters, the fine print. So, and at last but not least, now I'm going to explaining you an exercise how to use this equation 3.2. So imagine that for some reason you are delaying an investment of $5,000. So you want to know if you are delaying that investment, that let's say that you want to buy a specific machine that it costs $5,000, and you want to delay it 4 years. So how much will that actually be? How will that repercute in if you actually are estimating this future value of this expense annually with this discount rate? So again, I mean, pretty much here you just plug the numbers, and as you can see that delaying this um, um, this investment, it will cost you about $1,200 a year if you are delaying it, or that will be the annual cost of delaying this investment. That's how much you at this point you are not spending on this. So so as you can see, actually all of these formulas, well, this is how to use these formulas, and this is something that you're going to be doing on your exercise. So let me actually put you a practical example, so we're not talking about Mini Coopers and so on. So let's say that you have a project A, and basically in this project A, here we're going to have a convention. Anything that is with an arrow going downward, it means a cost. So everything that's with an arrow downward, this is a cost. Everything with an arrow upward, it means that is a benefit. Okay? So in this case, for project A, you have a capital cost, and imagine that what you're going to be building is a pumping plant. Imagine that you want to build a pumping plant for a specific water agency that you want to estimate two different projects to build a pumping plant. Okay? So here you have your pump house and so on, and water coming out of here, out of the pump house. So this project A, the capital cost to build all the infrastructure and drilling the well and so on is about $525,000. This is this capital cost, this initial investment, and it is only one time. And then the operation of maintenance for that specific layout of pump and infrastructure is going to be about 26,000. There is no salvage value, and the life expectancy of this project is 50 years. Now, project B, actually, when you're the pump house and the pumps are actually a little bit less expensive than the first one, $312,000. However, um, the annual cost is $48,000 every year. At the end of this has a life expectancy of 25 years. So at the end of these 25 years, you sell some of the equipment here and then do all over again. Buy the same equipment, do the same layout, have the same operation and maintenance cost, and again save it. So in this case, when you are thinking about these two, so which one would you choose? Would you choose alternative A, which has a higher capital cost but less annual operation and maintenance? Or would you choose alternative B, which is basically a less initial investment by a high or a higher operation and maintenance cost? So actually we can do the numbers and we can estimate. In this case, this specific method is to compare two projects. Okay, so in this case, what I'm going to be doing is for let's just start estimating. Well, for this, I'm going to estimate what is the cost of these two, and I'm going to select the one that is the cheapest. So that's the bottom line. So let's start estimating the cost of alternative A. So in order for comparing these two, we have to compare apples to apples. And in this case, for comparing apples to apples, what we are going to be comparing is the annual cost of project A, and we're going to compare the annual cost of project B. So once these two numbers are analyzed, then we will compare how they we will define which one is the least expensive, and then we're going to select that. So in this case, so what is the annual cost? And in this case, when you're talking, oh, okay, so we're going to be converting everything to annual cost. So I need to be using either equation 3.1 or 3.2. So in this case, this for this capital cost, initial cost, I'm using equation 3.1 with an interest rate of 8% and a 50% year life expectancy plus $26,000 every year, which this value is already analyzed. So in order to To account for this, well, now I'm plugging the numbers of these values in equation 3.1, which is basically, I mean, I'm just putting all these values as this equation is I specified. The value of this part is roughly 43,000. And again, I'm just, this operation and maintenance, it was already analyzed, so you don't have to do anything. When you add these two, the cost of alternative A is roughly $69,000, the annual cost of this. Now let's compare this with project B, which is basically um, what I'm going to do in project B is I'm going to estimate the cost of this part. And if I can get the cost of these first 25 years, it is exactly the same cost, that the same annual cost that you will have in the last 25 years. So that's what I'm doing here. Now again, for this capital cost, I'm using equation 3.1 with these values. The operation and maintenance is already the same. It's already annualized, and this 50,000 that you are saving at the end of these 25 years when you are selling all the junk and trying to recover, or selling some of the equipment and trying to recover part of your investment. In this case, this is a future amount of money that you're going to receive, and you want to convert that future again, in this case, because it's upward, these future benefits in an annual value. So in this case, what you're going to be using, or I'm using, is equation 3.2. So this first term is this, is what you're seeing here. Okay. Again, the operation and maintenance is already analyzed. So I'm just putting in here. And the last term, this one, is $684. So at the end, this is the cost, the annual cost of alternative B. So, dun, 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 dun. What is the results? Again, once we have annualized the cost of alternative A is $69,000, and the annual cost of alternative B is $76 and a half thousand dollars per year. So again, in this case, when you are doing this for these two options, well, you compare, and the one that you select, because it's the cheapest one, is alternative A. So again, as we started this exercise with all these different um, variables and so on, in this case, once you do the cost analysis, alternative A is the one that is um, uh, the least expensive. Okay, so in this case, we can think about a lot of these things as actually having, usually this is how a project looks like, and this is, I mean, moving out of these kind of um, more kind of educational examples, you usually see the benefits that they will not start as you start your operation of a specific project. So the benefits, you can actually estimate it, some of those in the future. And usually what happens with a project is that you need to have a specific capital cost that we call C sub O, or C sub 0, and then an operation and maintenance and sometimes recovery cost, which is usually an annualized value that we think. So in this case, we can actually, each of these benefits, actually move it into the present. And once you have moved each of these tiny ones one on top of each other, then you add all of them, and you obtain the present value of all those costs. Similarly, for all these different costs, well, basically you, as we did before, I think in this case you use this is equation 3.1 to this capital cost, do it in an annual, well, convert it into an annual cost plus the operation and maintenance, which these two are already annual costs. So in this case, what we are obtaining is the annual cost of a specific project. And once you have moved all of these values, as I mentioned before, into the present, then this present value, you annualize it. Again, in this case, using the same equation that we have down here, equation 3.1. And once you have these two annualized, then you compare the annual benefits and how these annual benefits um, are compared, excuse me, versus, oh, sorry, um, how these annual benefits are compared versus these annual costs. Okay, so that's basically what you're comparing here. And again, if we can think that if the net benefits are greater than 1, then it's economically feasible. Or if the benefit cost ratio is also greater than 1, then it is the same. You have the benefits outnumber the cost, so the projects are, in this case, economically feasible. So this is actually the discount rate of that the federals use, and you can actually Google it. So the average rate of interest, so what is this kind of discount rate for federally projects, is the average rate of interest on government bonds with terms of 15 years or more. And this is something that actually is accessible and that people use it to estimate all these numbers. So this is important because basically in one of your exercises you will be calculating this with two different alternatives. So what I mentioned here in the previous example here, make sure that you understand it pretty well because I'm going to be asking you this in your exercise and also in the exam. So benefit and cost. So let's talk about these two guides. So first of all, we want to calculate this cost and benefits because we want to express things in similar units, and in this case is in dollars. Um, compare, we want to compare each alternative, and actually how you approach the cost. What is your viewpoint, your perspective on how to estimate costs and benefits? It's really important. Um, some groups are more concerned with the benefits, and in this case, it can be hydropower, it can be agriculture, and so on. Some other groups might be more worried about or concerned about the cost, the environmental cost, and so on. Um, well, basically, in this case, we really want to compare different alternatives. It's not that you know for sure what you want to do in terms of building infrastructure or expanding infrastructure or a specific restoration project and so on. So in this case, you really want to compare alternatives. And in this case, what is the opportunity cost? And in this case, it might be the net benefits foregone if the choice of given the choice of one expenditure or one alternative compared to the other. Um, so usually, what is the cost of alternatives? You can think about direct cost, and that is straightforward. What is the capital cost? What is the initial year investment? How much do you have to pay initially to get things going? Acquisition of land, materials, construction, opportunity costs, and so on, and the operation and maintenance, and sometimes the replacement cost. The indirect cost of each alternative, it can be, I mean, a regular indirect cost rate because of managing part of this project or the cost to the environment. And there are certain valuation techniques. You pretty much, for the cost, well, you go and see what is the market value of this cost and operation maintenance. And sometimes the benefit for revenues from future deliveries of, in this case, of water, let's say. Um, what if there is no market value? Well, then you do what we did before, which basically evaluate what is the cost of the cheapest alternative, or you try to figure out if values can be estimated in other ways, and again, kind of the what is the foregone value. Um, Things to consider, and this is important. Investors, they prefer an early return on their investment because they can make more decisions or decisions faster for that they are going to be in the future. Um, Benefits and costs at different times must not be compared directly. You need to put it again, apples to apples. Move everything that you have into an annualized format. And sometimes for doing that, you have to move future benefits into present value. And again, once you have that present value, into an annualized benefits. Um, so now the previous what I was just the previous exercise, it was what if I have option A and B. I'm just comparing two um, two options. In this case, what I'm going to be comparing is two or more. And what is the rationale behind it? So as you can see, actually, scientists have a hard time naming things. And in this case, we're going to be estimating the incremental benefit cost. So what does this mean? That you have two projects and you want to know what is the if the increment benefits of project A versus project B outnumber the cost of going from a cheapest project A into a more expensive project B. So again, when you're comparing two or comparing three or more, what you really want to know is that the extra money that you are investing, it is actually, well, the benefits that you are receiving, actually those benefits outnumber the extra money that you are paying for going from a less expensive option to a more expensive option. So that is the rationale behind this. Now, in this case, what I'm going to be doing again is this incremental benefit cost. Similarly, likewise, the exercise that I did on optimization methods, um, these are the steps that you have to follow. First, for each alternative, you have to define the consequences. And in this case, the consequences are to estimate the value of benefits and cost. This is really important in an annualized value. Every time that we're going to be this type of analysis, this type of method, you have to move everything into an annualized value. And that's why the equations that I give you at the beginning, they are very important. Then you estimate the benefit cost ratio. And if there is anything that is less than 1, then is discarded. Why? Because it is not economically feasible. The costs outnumber the benefits. Then you actually you order the alternatives from alternative, let's say A, that is the cheapest, and you start ordering them in terms of the cost to alternative N, that might be the one that is the most expensive. So you will have to order all of them. Why? Because you really want to compare that if the extra cost is worthy, so you are receiving more benefits. And basically what we're going to be doing is select the lowest alternative cost is called the best. And the next higher cost is going to be called the contender. So this is project A and B. Then you compare best versus the contender. And basically we're going to estimate again if the increment in the benefits, and the increment in cost. And once we have done that, if this incremental benefit, this ratio of incremental benefit over incremental cost is greater than 1, then this who was the contender, it becomes the best. And then if you go and do the same for the rest of the alternatives, and at the end, once you have analyzed all of them, the current best is preferred alternative. And this part I'm going to show you how to do this. So let's say that we want to protect um, a specific town over here. So we have here a city, or it may not even be a city, it might be some small farms, or I don't know, one specific property. So imagine that you want to protect the people that lives down here. So there are there are some of the alternatives are to build a large dam, to build a small dam, or to build some levees. In fact, what we can do is to estimate only building the big reservoir, or only building the small reservoir, or only building the levees, or building the large reservoir and the small reservoir, or building the large reservoir and the levees, or building the small reservoir and the levees, or ultimately building the three of them. So which one is the most cost effective? The other thing is that for dams, the life expectancy is 80 years, and for the levee is 60 years. And actually, some of these are standard numbers. The discount rate, again, is 4% per year. And which alternative would you choose? So this is how actually I'm going to give you the numbers and what you want to start for doing this specific analysis. In this case, what is the capital cost? Well, for dam A is 6 million, B 5, C 6 million. For building A and B, so basically I'm adding 6 plus 5, and these are 11 million. For A and C, I'm actually adding 6 plus 6, and that's what I'm having, 12. Similarly, B and C, it will be 6 plus 5, these two, so it will be 11, and A, B, and C, it will be 6 plus 5 plus 6 is 17. Okay, this is the operation and maintenance, and it's exactly the same. When you calculate this operation and maintenance, this 17 comes actually of adding 0.9 plus 0.8. This 0.19, it comes from adding A and C, which is this plus this. Okay, and now in this case the do nothing project, the flood damage is already estimated at 2 million per year. But when you run all these different configurations in a model, into a reservoir and then hydraulic model, then you start seeing that what you estimate for only building dam A, it will be about 1.1 million of damage, annual damage, 1.3, 0.7, and so on. So as you can see, as you're building more and more infrastructure, you are actually reducing the flood damage. But is it worth it to do all of this, or is there any sweet spot or any combination of policies that you may think that are the ones that provides you the more benefits given the cost that these alternatives have? So in this case, for estimating the cost, what I'm doing is actually I think this is equation, yeah, this is equation 3.1, what you're seeing here. So in this case, I'm using equation 3.1. What that means is that for option A, for dam A, basically we know that this dam cost 6 million. So it is 6 million. It has a 4% interest rate. And as we were thinking, the life in years is 80. Okay. So actually, let me write this one down. Let me write it here. Again, so it costs 6 million. Sorry. the interest rate is 4%, and the life expectancy is 80 years. Okay, so with this information, you plug this information into equation 3.1 and you get that the annual expenditure of the annual cost, the annual capital cost, it will be $0.251 million per year. Similarly, for dam B, it costs 5 million. Again, this is the same interest rate, 4%, and for 80 years. So if you plug all of this again into equation 3.1, this is what you're gonna get. And for levies, actually this costs 6 million, the same interest rate, but, sorry, here 6. In this case, the life expectancy is 60 years. So you plug this into equation 3.1 and this is what you get. Okay? Now, once you have get these three numbers, so what is the annual capital cost of this? Well, you add, again, for this policy that includes the two large reservoirs, well, you just add these two, and basically you get 460. Similarly, for this is when you add A and C, when you add A and C. And likewise for the next of them. The operation and maintenance, well, basically that is already given. So the total cost of all these different configuration of options is when you add this capital cost plus this operation and maintenance, then you get this. Again, this capital cost plus the operation and maintenance, and you're gonna get this value. So similarly here, when you add this 2.65 plus 0.1 is 368, and so on. Okay, so now we have estimated the cost, and we're still in step 1. What about the benefits? So in this case, the benefits, so the do nothing, we're going to be comparing what are the damages and how do these damages compare to the do nothing. So the difference between these two are actually the benefits, the amount of money that you're not expending. So in this case, these are the damages of do nothing, and these are the damages of each of these alternatives. So in this case, when you do this, so subtract this column 1 minus 2, so that's actually, I'm telling you how we're doing this calculation for the columns. So column 3 is equal by subtracting column 1 minus 2. Similarly here, and again in this case, this is by doing nothing, and if you build this reservoir, then you expect 1.1 million. So the difference between these two, which is 0.9 million, is actually the benefits that you're gaining because of building this reservoir, and so on. So far we have finished step 1, which is basically estimating the costs and the benefits. Now, step 2 relates to rank. Once you have all of these things, take a look at the cost. Look this carefully and organize all your alternatives based off from the cheapest all the way down to the most expensive. Could you see that in this case the cost is increasing? So that is step number 2. And now we're going to be comparing first, in this order. And basically what we want to know is that given that you are spending more, the benefits outnumber this extra cost. So now let's start doing step 3 and 4, which is basically, well, first, this step number 3 is how to initialize this method, which is basically the do nothing it starts as, right now this is your best option, and you are using the second most expensive, which is building dam B, which this is going to be your contender. This is to start comparing all of this. So now that we have done that, well, in this case, if you compare the benefits minus cost, because these are 0, well, then you will have this is going to be undefined. So in this case, it's 0, 0, and 0 over 0. This is undefined. So that's why we just leave it there. For option B, this is the annualized benefits and annualized cost. So what do? You divide benefits, you obtain the benefits cost ratio, so basically dividing the benefits over the cost, and it gives you this, the benefit cost ratio. And if this is greater than 1, then we know that this is economically feasible. So at least we need to take a look at it. If this was less than 0, then we don't even look at it. We don't follow with the next steps. Now, how does these increments of benefits are calculated? So you subtract these contender benefits minus the best benefits, and this is 0.7. Sorry. Now, you do the same for the cost. You subtract the contender cost minus the best cost, and in this case is 0.298. So the um, increment benefit, the increment net benefit ratio, so the increment benefits over the increment cost, when you divide these two, it will give you this number. And if this is greater than 1, as you can see here, if this ratio is greater than 1, then the the contender becomes, this guy will become the best. So basically we know that do nothing is not an option, that the contender, well, in this case the new best, it provides you the benefits outnumber the increment in the cost. So the incremental benefit cost is greater than 1. Well, let's now the next, so we have analyzed this and this. The next one that now we need to analyze is alternative A. So again, this is our best, this is our contender, and this is what we're going to be doing. So in this case, we know that these are the benefits, these are the costs. We divided these two, and this is this benefit cost ratio. If this is greater than 1, then okay, we just keep looking. The increment in the benefits is 0.9 minus 0.7 is 0.2. The increment in the cost is the subtraction of these two, 0.52. The incremental benefit is dividing these two. So again, when we do this ratio, if the increment benefits over the increment cost is greater than 1, again in this case A, this, when I'm writing this, is that A is preferred over alternative B. This A greater than B, what this is not greater. What in the context of this analysis means is that A, this, it means that is preferred, is preferred over, as I'm mentioning there. Okay, so our new best is option A. Now, and in this case, you will have to continue repeating this. See, similarly, these are the benefits, these are the costs. If you if you obtain the benefit cost ratio, if this is greater than 1, then you need to keep looking. The increments in the benefits is 0.4, the increments in the cost is 0.25. When you obtain the incremental benefit cost is, in this case, is this much, which is greater than 1. So once again, alternative C is preferred over alternative A. So this is our new best. Which is the following contender? So we have, this is now our current best. And now we're going to be comparing against AB. So similarly, This is the increment in the benefits. This is the increment. Actually, there are no increments in benefits. Actually, this, as you can see, it provides does not provide a greater benefits than only the levies. So this is why this is negative. Sorry, I kind of moved myself ahead. So first we need to do the benefit cost ratio. So these are the benefits and these are the costs. So when we do this division, which is this is greater than 1. So it means that this one is economically feasible. Now when we are comparing the benefits, so doing this subtraction, this is when we are seeing that these benefits are actually no greater than the ones only with the levies. So that's why this is a negative value. This is the difference between these two, and when you do this, it's equal to this. Now this is actually less than 1. And what that means is that still C is a policy that is preferred over policy AB. Now the next one, so in this case, sorry, we evaluate an AB, still C is preferred over, sorry, this is a check mark, but I'm very bad drawing on this. So now we need to compare C against BC. So again, now we're comparing C. Again, BC, this is the benefits, this is the cost. You divide these two, is this third column. If this is greater than 1, then again, this is economically feasible. Then the increment in cost is subtracting this minus this, which is 0.2, and this minus this, which is this is the increment in cost. When you obtain the ratio, you obtain this 0.69, which again, this is less than 1. So still C is preferred over BC. Now we need to compare C and AC, which is this. So basically we're comparing this, well, AC again, these are the benefits, these are the costs, you divide these two. If this value is greater than 1, then it's again still economically feasible. The difference between 1.3 and 1.6 is 0.3. The difference between these two is 0.34. When you do this division, is this value, and again, this is less than 1. So still C is preferred over AC. And so you cross out this one, and then you need to compare the last one, which is C over ABC. These are the benefits, these are the costs. Again, when you divide these two, these are greater than 1, so this is an economically feasible option to look at. This is the increment in the benefits, so 1.75 minus 1.3, these are the increment in cost. If you do this division, it's again less than 1, meaning that the increment in the cost outnumber the increment in the benefits. And in this case, again, C is preferred over ABC. So as you can see here, our policy that we will choose over all of them, it will be project C. So this is how you compare a lot of these projects. Anyway, this is the incremental benefit cost method. So as you can see, that's a little bit lengthy, but I know that you can do it. Okay, so this is it for today. I hope you have enjoyed this lecture, and I'll see you in class back. Take care, and anytime that you have any question about your exercise assignment, well, you can always come back to this video and take a look at how this is done. Thank you so much. See you.